Imagine for a moment the vast, silent expanse of Mars. Picture a landscape scarred by ancient rivers and bathed in an alien sun. And there, against that backdrop, sits humanity's most sophisticated robotic explorer, the Perseverance rover. It's a marvel of engineering, a testament to our insatiable curiosity, designed to seek out the faint whispers of past life and gather samples that could unlock the secrets of another world. The journey to that red planet was an unparalleled ballet of precision, speed, and immense computational power. From its launch atop a mighty rocket, through the harrowing 7 minutes of terror during entry, descent, and landing, to its first tentative roll across the Martian soil, Perseverance represents the pinnacle of modern space exploration. Billions of dollars, years of relentless work, and the brightest minds on Earth converged to create this dream machine. Yet here's a fascinating, almost ironic twist in this tale of future exploration. Some of the most critical aspects of this cutting-edge rover rely on technology that, by Earthbound standards, could be considered ancient. We're talking about components whose lineage stretches back to the very dawn of the personal computing era, to a time when dial-up internet was still a novelty and portable CD players were the height of cool. It's a paradox, isn't it? The most expensive, sophisticated rover ever constructed, venturing into the unknown, powered in part by the echoes of the 1990s. Let's delve into this intriguing detail. At the heart of Perseverance's avionics, the system responsible for handling the entire electrical architecture and flight control, lies a very special microprocessor. It's called the RAD-750. This isn't just any chip. It's a radiation-hardened version of an IBM PowerPC, a design originally conceived by Motorola and IBM. If you were to compare its raw processing power to a desktop computer from Earth, you'd find it performing at a level akin to a circa 1992 Pentium 1 chip. Yes, the same kind of computing power that powered games like Doom and Myst on your grandfather's beige box is now helping navigate a nuclear-powered vehicle across Mars. The immediate question that springs to mind is, of course, why? Why, when we have supercomputers that fit in our pockets, would NASA's Jet Propulsion Laboratory, JPL, choose such seemingly antiquated technology? The answer, like so many things in the realm of space engineering, is elegantly simple and profoundly practical: reliability. As Richard Reiber, a JPL mobility flight systems engineer, put it so clearly, the closer you pack your transistors, the more susceptible to radiation you get. And in the unforgiving environment of deep space, radiation isn't just a concern, it's a constant, invisible threat that can scramble data, corrupt systems, and bring an entire mission to its knees. The RAD-750, despite its humble processing speed by today's standards, is a hardened veteran. It's battle-tested, a phrase that carries immense weight when you're hurtling a billion-dollar machine through the cosmos. This chip has been on hundreds of missions in space. It's been exposed to cosmic rays, solar flares, and the sheer vacuum of space, proving its mettle time and time again. When the stakes are this astronomically high, reliability isn't just a feature, it's the mission itself. It embodies the old adage, if it ain't broke, don't fix it, especially when you're building an unprecedented vehicle with countless other truly novel issues to address. But the RAD-750 doesn't work alone. This old-school computer works in tandem with a series of what are called Field Programmable Gate Arrays, or FPGA. These FPGAs are specialized chips that can be reprogrammed even after they've left Earth, offering incredible flexibility. Together, these systems control the rover's drivetrain, its 6 robust wheels, the intricate suspension system, and its myriad of cameras, which provide us with those breathtaking images from Mars. One particular FPGA, a Vertex 5, also has a story of quiet heroism. While perhaps a bit technologically dated compared to the latest commercial offerings, it too possesses that most coveted trait in space hardware: trustworthiness. This particular module was given a mission-critical straw. It assisted directly in Perseverance's successful atmospheric entry, descent, and landing. Imagine that! The delicate ballet of retro rockets firing, the sky crane lowering the rover, all orchestrated in part by this unassuming, battle-hardened chip. Now that Perseverance is safely on the ground, this very same computer system will be reprogrammed from Earth to perform a whole new set of tasks, specifically focusing on mobility, visual processing, helping Perseverance see and navigate its complex environment. So, as we watch Perseverance explore the Jezero crater, collecting samples and sending back incredible discoveries, let's take a moment to appreciate the unsung heroes within its metallic shell. The Rad 750 and the Vertex 5 aren't just antiquated bits of silicon, they are monuments to the enduring power of proven engineering, a testament to the wisdom of choosing reliability over flashy novelty in the most extreme of circumstances. Their story reminds us that true innovation isn't always about building from scratch, but sometimes about expertly adapting and trusting what has stood the time, even as we reach for new worlds. It's a beautiful lesson in engineering and in life, isn't it? That what's old isn't necessarily obsolete, and that tried and true foundations can empower the most ambitious of new ventures. What are your thoughts on this blend of old and new in space exploration? Do you find it surprising, or does it make perfect sense? Share your perspectives in the comments below, and let's continue to marvel at the ingenuity that drives us to explore.